Hello everyone, once again, thanks for tuning in and I hope you are doing well. This video will be an introduction to the polar coordinate system, alrighty, as opposed to the one you're more familiar with, which we call the rectangular one, although you may not have ever seen that name because there was no need to really name it. It's just our XY axis. It's called a rectangular coordinate system. We are going to study a polar coordinate system. But first, let's take a look at a point in a rectangular plane, and I'm sure with very little effort you can name the coordinates of that point, 4, 2. That is because that point is located 4 units to the right and 2 units above the origin of our coordinate system. So in a rectangular coordinate system, which it's also called a Cartesian coordinate system, our values, our coordinates are based on a horizontal and vertical distance away from the origin. However, those 2 points, horizontal and vertical distance, are not the only attributes that that point possesses. And here's what I mean by that. Let's take a look at that point once again. But now, instead of considering its horizontal or vertical distance away from the origin, think about this. It's actually also got this diagonal, or maybe a better word would be Pythagorean distance away from the origin also. That is a quality that that point possesses. It also possesses, if you think about the line that I just drew there, that R, that line, that diagonal distance, as being part of an angle in standard position, there's also an angle there that that point possesses. So rather than use 4, 2, what we're going to use for a polar coordinate system is just the numbers r and theta, where r is kind of a Pythagorean distance, let's say, from the origin, and the theta is a standard position angle from the x-axis going counterclockwise. That's what standard position means. Okay? So those 2 coordinates, r, theta, are different coordinates for that exact same point that we were just calling 4, 2 a little while ago. So let's look at an actual polar coordinate grid. All right, it looks something like that. And on a polar coordinate grid, we have something called the polar axis, which is what you would usually call the positive x-axis, and the origin is given the name the pole. Okay, that's just that's what they're called, polar axis and the pole. All right, so if I pick up, the angles are still measured in standard position, positive angles going counterclockwise and negative angles going clockwise around the circle. So let's pick a point. I've named a point up there, and you can see that the angle for that point away from the polar axis is pi over 4, and that the distance is 6. Therefore, the coordinates of that point are 6, pi over 4. Sound pretty simple? It actually is pretty simple once you get used to the system. Here's another point over here in quadrant 2, and you can count pretty easily there. The distance is 3, and the angle is 2 pi thirds. Therefore, 3, 2 pi thirds for that point right there. Here's another point down there right on the vertical axis there, and that's 5, 3 pi halves. So you'll notice that I've picked 3 points all around this pole here on our polar coordinate grid, and none of them have negative coordinates. So you may be asking yourself, is it possible for polar coordinates to have negative values? And the answer is, of course, yes. But let's take a look at how that works. So here's a point down there in quadrant 3, and of course, with the little bit of practice you've had already, you can count the distance away from the pole, and you can figure out that angle, and that point's coordinates are 5, 5 pi over 4. And it won't be too surprising to you that to learn that we can also measure the angle in the negative direction. That would be negative 3 pi over 4, and therefore another pair of coordinates for that same point are 5, negative 3 pi over 4. Okay, so there's a negative theta value, and that's, like I say, not too surprising or different from what you've been already used to. But how could r be negative? Well, let me give you a couple of other coordinate pairs for that point. I'm going to erase those angles there, and that same point could have these other coordinate pairs: negative 5 pi over 4 and negative 7 pi over 4. those are two more coordinate pairs that name that same point down there in quadrant 3. Okay, so how does that work? How can the angle be pi over 4 or negative 7 pi over 4 for that same point? Well, think about where is that point? Or where is that angle, excuse me? It's up there in quadrant 1, right? There's pi over 4, negative 7 pi over 4, of course, names the same position on the grid. So look what happens there. When I use those angles up there that are on the opposite direction from my point, my radius becomes negative. And that's basically the rule there. A negative r value means that the point is located in the opposite direction from the named value. Now that may take a while to sink in, so let's take a look at another example of this same idea. There's a point right there over in quadrant 2, and you can name the positive r value points or coordinates for that point: 6, 5 pi over 6, or 6 and negative 7 pi over 6. Those two angles name the same place. Now think about the angle that's 180 degrees or pi radians away from that point. That would be either 11 pi over 6 or negative pi over 6. Both of those numbers name an angle that is exactly in the opposite direction from 5 pi over 6. So therefore, another pair of coordinates for that same point are these two pairs right here: negative 6, 11 pi over 6, or negative 6 and negative pi over 6. Again, all four coordinate pairs there name the same point. All right? Now, why do polar coordinates do this? This seems very confusing, very strange, to have more than one possible coordinate pair name the same point. That doesn't seem like a very well-designed system. And the reason will become clear later on. I'll just give you kind of a quick sketch of why this is done. It's not done just to confuse people. I know a lot of mathematics seems like it's done strictly to confuse people, but that's not really true here. In polar functions, which we're going to get into a little bit later on, very soon, polar functions usually use trigonometric functions. All right? And in trigonometric functions, well, in this case, the r is dependent on theta. So you'll see this when we start actually listing and studying polar functions. But r depends on theta, and it is possible, depending on what theta is, excuse me, for r to be a negative value. So we have to have the possibility of radius, or r, being a negative value, even though that may seem at first very counterintuitive. Okay, well, I hope this was a decent enough introduction. With a little bit of practice, you guys will get the idea here of how polar coordinates are named. Okay, thanks again for tuning in. Stay tuned, and we'll talk to you soon.